Welcome to e2e9CgbT7C0 Lecture 6. Woo! Oh, come on. Welcome to e2e9CgbT7C0 Lecture 6. Woo! What happened to you? I left for a week and now you're all like all tired? What happened? And where's everybody? There's supposed to be about 58 student register for the class. For those of you who are only going to listen for it on webcast, there are going to be some points where I'm going to stop the microphone and I'm going to say things only for the class. So you have to be updated somehow. And when I do board work, you won't be able to see it, or you'll be able to see it as a mirror, depending on how it works. You'll see what I mean later today. Okay, so I apologize again for being away, but I'm back with a bug, but hopefully I'll get rid of it soon. So I'll just start with a few announcements. So homework 1 solutions are posted. How is homework 1? I don't see. I mean, what does it even mean? Is it hard, easy? It was okay. Okay. This is kind of a typical, effort that you'll have to put in the homework. Maybe a little bit on the heavier side, just to weed through some of those that are watching online. Self-grading is due on Tuesday. Okay. Homework 2 plus lab 00 are due on Friday. Okay. There's going to be a lab bash. Where's Frank? Not here. Okay. We're going to post probably on Thursday. There's going to be a lab bash to help you set up. So it's going to be a couple of hours, hopefully, and it's going to be on Thursday. Okay. We're going to have a homework slip policy of lowest grade homework will be dropped. Okay, so pick and choose, but don't pick and choose in the beginning because you'll have a problem later. Okay, just one we're going to allow you to drop, but that's it. Okay. Wednesday we're going to give SDRs, the software-defined radios, so you can start playing with them. The first lab we're going to be using them is going to be 2 weeks from now, so that should be a lot of fun. It's going to be monitoring signals coming from airplanes that they transmit their position. So you'll be able to pick up those signals and demodulate them and try to detect packets and then be able to decode them and put the position of an airplane on a map. Okay. You have to. So about reading. So please read through the book. We're covering some material, the material, but actually the material in the book is the one that we're going to test you on. So it's a little bit more, especially the chapters that we're going to do a review on. Of course, we don't review everything, but we expect you to know, for example, the Z-transform. We spent one lecture, but there's a whole chapter there, chapter 3 in the book. So please go. I want you to start finishing chapter 8, which is DFT, I think, and then start reading chapter 9, which is FFT, which we're going to start talking on Wednesday. Another announcement, ham radio licensing lecture. So tomorrow I'm going to start giving a series of lectures to prepare for the ham radio licensing exam. These are optional, but I do recommend everybody to come. It's actually lots of fun. If you can make it, 6:30 to 8 p.m. I'm going to post the lecture notes on B courses, but they're going to be sparse. Right? But the idea is also that you look at the book, you read through the book, and then solve questions so you'll be able to pass the exam. It's really a lot of practicing questions, yes?
How many lectures are there?
I think it's going to be 5. So, 5 lectures. Yeah. Yep.
Is it worthwhile coming if we're already licensed?
Oh, you're already licensed? Oh, that's awesome. Are you a technician or general? Or? I mean, you want to teach? Yeah, no, then you don't need to, because if you have already a license, then that's fine. Very good. Anything else? But if you want to participate in like demos and stuff, then I'll be happy to take on that. Get some help. Okay, I have office hours announced Friday 11 to 12. So all the last minute folks, I'll be there to save you. Hopefully, I don't know, maybe. And it's going to be in Corey 506, my office. So I didn't write it, but it's on the. Can it be 12 to 1? No, I can't. Unfortunately, I can't. I'll see what I can do. Why? This particular. Yeah. I'll see what I can do, but probably. I don't know. I might be able to stay a little bit more, maybe 12:30, but I have usually a meeting at 12:30. Midterms are scheduled now. First midterm is going to be on the 20th, so 2 weeks from now. So it's coming up. But mostly it's going to cover all the materials that we, the overview, the review material, including DFT, FFT that we're going to cover, frequency analysis using the DFT, and then also time frequency, okay, that we're going to cover. So anything that we'll cover up until a week before the midterm. Other midterms a month later, and then a month and a week later after that. So it will give you about 2 weeks to do your projects, which I think is it's a good amount of time to invest, and you're going to be done with the class, so you'll have like fresh mind. Ignore all the rest of your classes and be able to work on the project. Yes?
So just to confirm, there's no final?
We will not, there will not be a final. And that's a final decision. Okay, ham radio exam, March 12th. Okay, remember that. Put it on your calendar. You will need to be licensed in order to do the project. So please go for that. Yes?
Will the ham radio lectures be podcast?
No, they won't be podcast, unfortunately. Pardon? It's going to be 6:30 or I think 7 to 10 p.m. or 11 p.m. depending how many people are going to actually take it. But it looks like there's going to be more than 60 students taking it, about 80. So you won't have a chance to retake it, so you need to pass the first time. Or go somewhere else and take the exam, okay, if you don't pass it. It's not hard. Last time we had 100% pass, okay, so keep the Berkeley, Okay. All right. Any more questions till we start actually the material for today? The projects? Project due on the last day of RRR week, the dead week. Okay, last day of either Thursday or Friday. Yes? CS170, when is it? 6:30. Till? 8. Yeah, I think you'll be okay. You can take it like at 8. So it's going to be all going on. So, yeah, I mean, there's always conflict, but this is really hard to schedule. So it's done. Yep. On Tuesdays, every Tuesday, 6:30 to 8 p.m. You don't need to come in order to take it. I mean, it's not that hard to study by yourself. It's helpful. I'm going to show some demos, get you all excited and thrilled about radios and stuff and signal processing, and it's going to be awesome. But if you can't make it, that's that's okay. Any more questions? All right. Cool Things DSP. So I went to this conference. It was a conference about last week. It was a conference about biological and astronomical signal processing. You would think what these have to do with each other. Turns out there's actually lots of common mathematics between astronomy and medical imaging, in particular using Fourier domain sampling. So MRI, if you remember, I mentioned that the measurements are sampled in the frequency domain. It's kind of like a fancy Fourier transform machine. In astronomy, it happens as well. But there's a lot of actually very cool signal processing that I've seen that I thought maybe I'll share some of it with you. It's kind of mind-blowing, the things that they do. And so anybody knows what this map is? It says, right? It's called the CMB, Cosmic Microwave Background Radiation. It's a map of the distribution of radiation in the universe about 300,000 years after the Big Bang. Okay? Turns out you can measure it today, okay, by looking at the microwave frequencies and basically looking at distribution of energy. It's just amazing, first of all, when, how, we're sitting on this rock, right? This really small rock in the universe, and we're trying to observe as much as we can. It's just amazing how much we can actually conclude just by observing the universe and observing nature. It's just mind-blowing. But what's amazing about this, so there was this period, the Big Bang. They don't really know what happened up until 10 to the minus 36 seconds. So from 0 to 10 to the minus 36 seconds, they don't know exactly what happened. But after that, there was a period where there was kind of this soup of, kind of a hot soup, right? There's lots of energy, lots of radiation. Basically, quarks kind of floating around. And everything expands. And then once things expand, there's this cooling down of the universe. The universe starts cooling down. And after 380,000 years, it cools down such that there's this period of recombination where electrons bind to protons and atoms form. Okay? Before that, the universe was opaque to radiation. Okay? Photons cannot propagate because basically there's all these free electrons roaming around that basically bounce photons around. So once there's this recombination, there's no free electrons. There's not that many free electrons in the universe. The universe became transparent to radiation. And this is the map that you measure at that point. Okay? The distribution of energy in the universe. Okay? Turns out it has Gaussian statistics. Okay? Due to quantum fluctuations. And the fact that it is actually not uniform leads to, with the help of gravity, to formations of stars and galaxies and so on and so forth. So a lot of research that is done on these maps that was observed by the Planck. This is Planck telescope, and it's just recent result from about a year ago. That was released. Very high resolution map of the microwave background radiation, and from that, people try to build models and try to model how this distribution would lead to star formations, for example. Okay, how you use that as a dynamic system, put gravity and all what we know about the universe, the rules of the universe, and see how this forms into galaxies and stars and so on and so forth, or clusters of galaxies. It's quite amazing. The other thing, there's a lot of things that people do on this, because we observe the skies, and this is radiation. Radiation is actually perturbed by gravity. So they try to look at distortions of the Gaussianity of this distribution and look at how gravity kind of distorts this field. And so from that, they can extract, for example, distribution of how much matter is there in a galaxy and so on and so forth, just by trying to calculate how much it deviates from this Gaussian distribution and so on and so forth. So there's a lot of cool signal processing that's done. It's actually quite amazing what you can do. I might tell you a little bit more about things that people do in this field. But just mind-blowing that you can actually make these conclusions. This, by the way, was observed by mistake by I think scientists from Bell Labs, and they just they got this noise, added noise that they picked up, and it was kind of like they pointed out antennas everywhere, and they kind of saw that noise everywhere, and they didn't know where it's coming from, but they really knew their equipment. They knew that that noise shouldn't be there, so they published a paper about this, but they couldn't explain it. And there was another group, I think at Princeton, that was actually predicted this type of radiation, and those folks in Dodge actually scooped them in getting the Nobel Prize for that. Well, I mean, what happened? Okay, all right, moving on. So you went over, so far we talked about the DTFT, right? We talked about linear systems, we talked about the DTFT. We talked about the DFT. Okay, so DTFT is the Fourier transform of discrete signals. Okay? When we have discrete signals, then the Fourier transforms become periodic. It's still continuous. We have omega as our variable. It is continuous. But it is periodic because we have a discrete signal. Just remember there's a nice analogy between, so anything that is impulsive in one domain, it will be periodic in the other domain. And something that is impulsive and periodic will be also impulsive and periodic. And you'll see that, for example, if you look at the impulse train function, right? It's impulsive and periodic in one domain. It's impulsive and periodic in the other domain. We talked about last time about the DFT and showed the relationship between the DFT and the DTFT. And in fact, the DFT are samples of the DTFT. Okay. But the nice thing about the DFT is that it is discrete, right? It's very easy to calculate. It is similar to the DFF, discrete Fourier series that you did cover probably in 20 or 120, and we assume that you went over this. There are some actually subtleties about the sampling that we're going to talk about probably next time, when it doesn't actually hold. So today what we're going to talk about are properties of the DFT and relationship between linear convolution and how you can actually compute linear convolution with DFT. And then we're going to prepare for leading towards the fast Fourier transform. Okay, so properties of the DFT are effectively inherited from the discrete Fourier series. And the only difference between the discrete Fourier series and the DFT is kind of like semantic. I would say it's same, but different. And it's a different conceptual idea. In DFT, we assume that our signal is finite. Okay? So it is. So we have a finite signal, and everywhere else it is 0. So if I have a 5-point signal, and I'm going to compute a 5-point DFT, I'm assuming that the signal outside of these 5 points is 0. That means that if I want to compute now a 10-point DFT on this 5-point signal, okay, would be like 0 padding the signal, as opposed to the DFS, in which we would consider the signal to be periodic, so with a period of 5. Okay, so it is semantic, but it makes a big difference. Okay, as you'll see. So the DFT is an orthogonal transform. You saw that last time. Okay, an orthogonal transform preserves information. Okay, nothing is lost by computing this transform. So all the information that is in one domain is preserved in the other domain, and you can go back and forth between those two domains, which is also an important property. DFT is linear. Okay, that means that if I compute, if I take two signals and I add them, and then I compute the DFT, it's the same as first computing the DFT of each of these sequences and then adding the result. Okay, it is a linear transformation. An important property of the DFT is circular time shift. So if you remember from 120, you talked about time shift. Okay, what happened when you shift a signal in time? You get a modulation or a linear phase in the frequency domain. Yes? Yes? Shift in time leads to a modulation in the other domain. Now, in the DFT, we're talking about a circular shift in time would lead to a linear phase in the other domain. Okay? But it's going to be a circular shift. So again, it's slightly different. Okay? By circular shift, I mean that if this is my sequence, this would be the analogy of the DFS sequence. Okay? This will be the sequence that we use for the DFT. A circular shift means that you shift. It's like shifting this in time, but then taking this sequence. Okay? So it's kind of wrapping on top of itself. Okay? So it's like shifting this sequence and then cropping it from 0 to n minus 1. Okay? So circular shift, wrapping around itself, would lead to a linear phase in the other domain. Okay? Very important property. Now, the opposite, if I have modulation in the time domain or the sequence domain, that leads to a circular shift in the other domain. Okay? So a modulation, e to the j 2 pi over n times nl, will lead to an L sample shift in the other domain. Okay? We're going to talk later about what does it mean when n and l are not actually integers. Okay? But we'll see that much later in the class. Okay? But for now, just consider when they're integers. Complex conjugation, so if you take the conjugate of your time signal or your sequence, then that leads to a conjugation of the other domain, but it also is circularly inverted. Okay? So you flip it around and you conjugate the value. And when I'm talking about star, it means that that's the complex conjugate. Okay? Conjugate symmetry for real signals. So this is a really important property, again. If I have a sequence, and the sequence is real, I can take this property. I can take this property, and once I make sure that x and x star are equal for real sequences, I get a conjugate symmetry in the frequency domain. Okay? Conjugate symmetry in the frequency domain. Now, what does it actually mean? From an information point of view, right? Let's say I have a 5 length sequence. I compute the DFT. What is the DFT of the same size sequence? I get how many numbers? 5, right? So I start with 5 real numbers, and I end up with 5 complex numbers. Count the number of numbers. That's twice as much. Doesn't make sense. I take a signal that has a certain dimensionality, just 5, right? I can represent it with a length 5 vector, right? And I end up with something that I can represent with a length 10 vector. So there has to be some redundancy. This is orthogonal transformation, right? I'm embedding a 5-dimensional signal in a 10-dimensional space from an information point of view, right? So there got to be some redundancy there. There got to be some symmetry that I can use in order to really exploit the fact that I have a lower dimensional space, right? It has to make sense, right? Because I'm going to go back and forth between them. There's no loss of information. It's exactly the same information. So there got to be some redundancy in the DFT of a real signal because of that. Okay? Does this make sense? Just from an information point of view. Think about it.
Why dimension should be the same if it's 5 to 5?
Well, you map something as real into a complex, right? So you have 5 real numbers that tend to be 5 complex numbers. If you think about, the dimensionality of representing those, right? I mean, what is really complex numbers? It's just you take I and I times the imaginary, right? So you can think of it as a 10 size vector, right? So it's bigger, but it must lie in a smaller dimensional space, okay? Because we start with something real, and so there has to be some symmetry there, and the symmetry. Let me try to. And the symmetry is really conjugate symmetry. So real signals turn out to be conjugate symmetric. And let me just show you what it means. Very good. That's great. And let me move that thing a little bit. Great. And like this, yep. Okay, so let's say I have a five point signal, right? So 1, 2, 3, 4, 5. Okay, this is the DFT of a real signal. Okay, this is the DFT. I'm talking about x of k. This should have conjugate symmetry. Where's the symmetry in this 5-point signal? Where's the symmetry? How do you look at the symmetry? Which one is corresponding to which? Okay, this is k equals 0. This is k equal 1, k equal 2, k equal 3, k equal 4, and I apologize for those watching it that see the opposite, inverted, but that's your fault for not showing up here. So, which is symmetric to who? How do you do this? Here's a trick. Okay, here's a trick. What I do is, you take this one. Basically, you do an extension of basically a periodic extension of the sequence. Okay, you do a periodic extension for the sequence. So you take k equal 4 and you put it here, and then you take k equal 3, and then k equal 2, and then k equal 1, and then k equals 0, and so on and so forth. Right. So I just copy and I replicate the signal. Okay, so this was this, and that, and that, and that. Okay? So now the symmetry is going to be around k equal 4 and k equal 1. Okay. K equal 3 and k equal 2. And that's pretty much it. Okay? So this is a way to see, how the symmetry would work like. Okay? So what does it mean, by the way, on k equals 0? If it's conjugate symmetrical with itself. It has to be real. Okay? Why does it have to be real? Let's think about this. What is k equals 0? It's the DC component. You add, what is the DC component? It's just the sum of your signal. Your signal is real. Got to be real. Right? So it makes sense that k equals 0 is real. Okay? The other ones are going to be complex. So for a 5-point signal, you got 1 that is real, and then 4 that are complex, with 2 pairs of complex conjugate. Okay? So k equal 2 and k equal 3 are the same. So it's the same as this one or this. Right? That's the symmetry. Okay? So this is one way to do this. What happens if your sequence is even? If your sequence is even, and you're not going to see this. Okay? This is 0. K equal 2. K equal 3. Remember what you do. You replicate it on the other side. Right? And this is k equal 3, k equal 2, and k equal 1. Okay? This is 0. So 0 with itself, 1 with 3, and then 2 with itself. Okay? So now, effectively, the conjugate pairs are k equal 1 and k equal 3, and k equals 0 and k equal 2 are real. Okay?
Why 1 and 3 are conjugated?
Just according to the property. If you actually, right? If you look at the property of the DFT, and you can get to that property very easily by basically plugging in this into here, you'll see that you're going to have a conjugate pair. Okay? And just if you count the indexes, just so you figure out, so there's going to be 2 real, if you have a even sequence, then you're going to have 2 real numbers, and the rest are conjugate pairs, complex conjugate pairs. For odd sequences, you're going to have one real and the rest are conjugate pairs. Okay? So this is one trick way to quickly figure out the indices. Okay? Any questions? Now, why, by the way, for an odd sequence, two components are real? What's the highest frequency that you're going to get for an even sequence? If you actually look at the DFT, you're going to end up with 1, minus 1, 1, minus 1. Okay? Because it's even. And again, you multiply that with your sequence. If your sequence is real, then you're going to end up with a real number. Okay? That's why you get two values that are real. Okay? Any questions? All right. So this is a very important property. Actually, we use it quite a bit. Like, for example, in MRI, we use it quite a lot. If you look at distribution of, spins in your body, I mean, it's a real quantity. So effectively, the image should be real, right? But we measure things in the Fourier domain. So there should be some complex conjugate property between, in the frequency domain that allows us to reduce the number of measurements by almost a factor of 2. Because we only need to get part of the frequency domain, and we can complete the other part by just using this conjugate property. Now, with MRI, there's systematic errors that cause the image actually to be complex, but we do some corrections, and we can actually get away with just a little bit over a factor of 2 in reduction of time. So we need to get a little bit more over that to get some of these corrections estimated. But we use this property. I think Julia showed you a single sideband communication. So this is another property where we use the same factor, this conjugate symmetry. All right. Parseval identity. What does it really say? What it really says is that the energy in one domain is proportional to the energy in the other domain. Okay? So the sum of the magnitudes squared in one domain is proportional by a factor of 1 over n to the sum of the square of the magnitudes in the other domain. Okay? And why is that? That's because the transformation is orthogonal. So there's a preservation of length, of energy, between the two domains. Okay? It's really easy to prove in matrix notations. Okay, so we showed you last time how you represent the DFT as actually a matrix, right? Which takes, if you actually compute the DFT as a matrix, how much operation, like what's the order of operation that you need to apply? Let's say your signal is size n. N squared, right? So if you actually use the matrix, the DFT matrix to compute the DFT that takes you n square number of operations, turns out that there is a way, by exploiting the structure of the DFT matrix, to reduce it to n log n. And this is the FFT algorithm, and we're going to go over it next time. Okay? So if we look at matrix notations, in one domain we look at x star x. So what is x star x? Is the inner product with a vector with itself. Basically, it's the sum of squares of the element of x. What is it really doing? Well, I can take the inverse, I can take the inverse DFT of x, of capital X, and here is the inverse DFT of capital X. Right? That will give me x. This will give me x as well. Okay, that's the inverse DFT. Okay, 1 over n omega star is really the inverse, right? Like we showed you last time. So this is how I write the inverse. So now I just need to track. I get 1 over n here, 1 over n here, so 1 over n squared. Okay. And then I've got conjugate of this, basically flips them and put a conjugate. So now it's x conjugate w sub n and w conjugate n times x. This turns out to be n times I. Why? It's orthogonal. That's right. When you take a matrix, right, that's orthogonal. Let's say a matrix A star A would be diagonal. That's the actually definition of being orthogonal. That means that every column is orthogonal to other columns. So only if you take an inner product with its own vector, that's when it's not going to have a zero value. Right? So that's by definition orthogonality. Okay? So each column of the DFT matrix is orthogonal to the other one. That's why when you do a matrix multiplication with its conjugate, you only get the diagonal elements. Okay? So this is n times I. So that, of course, leads to 1 over n x star x, which is exactly what you see here. So it's really easy to prove using matrix notations. Okay? All right, circular convolution. Circular convolution is an interesting property of the DFT. Again, we're talking about circular stuff, circular shift, circular convolution. So the circular convolution between two sequences is defined in the following way. It's effectively, you flip one signal and then you slide it around. But you flip it and it's kind of like sliding it in a circular way as opposed to with usual linear convolution where you just flip it and run it. Now you kind of circularly run it around it. I'll show you what it actually means. Circular convolution is also commutative, much like linear convolution. So the circular convolution between x1 and x2 is the same thing as x2 and x1. And this is how it works. Okay, so let's say I have two sequences, x1 and x2, and I want to compute the circular convolution of size 7. Okay, of size 7 of these sequences. Then effectively, I circularly flip that signal. Okay? So I circularly flip that one. So now it's inverted and goes backwards, and I color-coded them. Okay? So you can see actually the order. So they're, there you go. Red, orange, yellow, green, blue, purple, right? But this is not ordered that way. Anyway. Sorry about that. I usually order them according to the color of the rainbow, but not this time. Okay, this is the order. So, yes? Well, I guess red, orange, green, yeah, it is actually order. All right. Okay, so then I circularly flip it. So you see the order is flipped, but it's circularly flipped. Okay? So it goes back and wraps upon itself. Okay? And now you multiply and add. Here, this is when you multiply and add, we'll give you y0. Okay? All right? Now, it's the same thing as doing a periodic convolution over a single period. Okay? So if you replicate the first signal and periodically extend it, it's the same thing as doing just a simple convolution over a single period. It's exactly the same thing. So that's another way that you can think about that. Okay? So I flip the signal, and then I do a convolution over a single period, and just look at this beautiful animation. Oh. Right? You see? And you multiply and add, multiply and add, multiply and add. It's just gorgeous. And then you're done, and you get your result. Okay? So this is a circular convolution of two sequences. Okay. So what's beautiful about circular convolution is if you compute the DFT of the circular convolution, you effectively get multiplication on the other domain. Much like with Fourier transform that you have, you take a Fourier transform of a linear convolution, it's multiplication of the Fourier transform, right? Now, if you have a circular convolution, you get multiplication of the DFTs. Okay? So this is almost useful because often would like to do linear convolutions, but we'll get to that. Okay? So multiplication will give us, circular convolution will give us multiplication in the other domain. Very powerful. As you'll see next time, this will relate to diagonalization of a matrix? Think about that. Because once you have something diagonal and you multiply with each other, I mean, this is like element by element multiplication. Okay? So you'll see that when you have a circular convolution, the DFTs are maybe eigenvalues, eigenvectors of circulant matrices, and the diagonalizes. It all relates to that. And I'm going to show you that next time. Okay? But when you have a circular convolution, you get multiplication in the other domain. We'll get to actually what's the implication in terms of linear algebra as well. Okay, if you have multiplication in one domain, in the sequence domain, you get a circular convolution in the other domain as well. Okay, with another factor of annoying factor of 1 over n that you have to remember. Okay, so linear convolution. We'd like to do linear convolution, okay? But with DFT, we can do circular convolution very easily, but linear convolution is the one that's useful. When we do filtering operations, we often like to do linear convolutions. So what we're going to do is we're going to show you how to perform linear convolution using circular convolutions, and then use the DFT to perform them. Now, why do I even care about performing using the DFT? If I could just compute a linear convolution. Could be faster. Could be faster, depending how you compute the DFT. Okay? But, so if it took you n square, O of n squared to compute a DFT, it won't be faster. But since there is a way to compute it, the DFT with n log n, then it is possible to do it faster. Okay, so we'll get to that. Okay, so how do we do linear convolution? We start with two non-periodic sequences. So we have x of n, that's of size L, and h of n, which is size p, two different size sequences. Okay, so for example, x of n could be a signal, h of n could be an impulse response of a filter, okay, of a FIR filter, finite impulse response filter. And we want to compute the linear convolution, right? That's a simple linear convolution between those, or linear convolution sum when we're talking about discrete signals. So the result is going to be yn is going to be non-zero for 0 is less than n for L plus P minus 2. And effectively is going to have a length of L plus P minus 1. So the size of the two sequences minus 1. Okay? That's the usual thing that you saw, I'm sure you saw before, right? Right? Okay. So I'm going to end up with a sequence which is size L plus P minus 1. Okay. In order to compute this, I need L times P multiplication. Why? Because I'm going to put a P signal over an L signal. Okay, so I'm going to multiply P times L times. Okay, so P times L. Okay. For every shift is going to be P. And how many shifts? L shifts. So L times P multiplication. Okay, so how do I compute a linear convolution via circular convolution? Well, all I need to do is make sure that there's enough zeros. If there's enough zeros, then when I perform a circular convolution, when I wrap around, those wraps are going to be multiplied by zeros. So all I need to do is zero pad my sequences such that it has enough zeros so even if I do circular convolution, it doesn't matter. It will just wrap with zeros. And that's the basic idea. Okay? So I'm just going to zero pad the first sequence by P1 minus 1 zeros. The second one I'm going to wrap, zero pad by L minus 1. Okay? So now I'm going to end up with two sequences that are the size of the result. Okay, of the linear convolution. So now these two sequences are going to be L plus P minus 1. Okay? That's all I need to do. Just zero pad them so they have zeros. Okay, so now the sequences are two length, and now we're going to compute the linear convolution using a circular convolution of length L plus P minus 1. Okay? So it turns out when you zero pad them, there's an equivalency between the linear convolution and the circular convolution. Here's an example. Okay, again, let's say I have a sequence with L equals 5 and P equals 4. So now I should end up with a sequence that's size L plus P minus 1, which is 8. Okay, that's the result of a linear convolution. I'm going to zero pad both of them to be of size 8. Okay. And now I'm going to compute the circular convolution, right? So I'm going to flip, right? Circular flip. And you see what happens when I circular flip it. When I circular flip it, with zeros, right? There's zeros where there's signal. It doesn't matter. It doesn't wrap because there's zeros. So it's exactly the same as doing a linear convolution, right? Because it's like zero extending it. I mean, this is basic idea. It's pretty simple, right? I spent like lots of slides to explain something really simple. Okay? So now the circular convolution of size 8 is equivalent to a linear convolution between those two sequences. Okay? So that's cool, right? Because these don't overlap. Okay. So in practice, we can implement circular convolution using the DFT property. Okay? So a linear convolution is equal to a circular convolution of size m. And I can compute it by computing the DFT of the zero-padded sequence, multiply by the DFT of the other zero-padded sequence, and then take the inverse DFT of the result. That's a circular convolution, which equals to this, but turns out that if I zero-pad it correctly, I get a linear convolution. Okay? So the advantage is that the DFT can be computed with n log n if we use the FFT algorithm. Okay? If we do that, then the order of computation for computing this linear convolution is still n log n. Okay? As opposed to L times P. Right? That could be significantly more expensive. And if the sequences were both the same size, then it would be n squared. Okay? If I just need to compute the linear convolution as it is. The drawback is that I need to wait for all the samples to arrive. So let's say x of n is really, really long. Right? If it's long, I have to wait till I get all the x's. Then I zero pad the h, I compute the DFT, I compute this, and then I compute the result. But I have to wait till I finish all the x's, until I get all the x. Okay? So if I do this, I need to know what all my sequence is in order to perform the filtering. So let's say I want to filter my voice, right? Let's say a low-pass filter of my voice in a real-time communication system. If I want to use the DFT in order to compute the linear convolution, I'm going to have a problem. Because, I have to finish talking. After I finish talking, you can filter it using the DFT fast, but you have to wait. So, it's incompatible in that sense. Okay? So there's got to be a huge delay between the two. So I'll finish here, but just anybody has an idea of how to actually solve it? Yeah.
Or a fixed number of samples, and then you process it in a fixed number of processes.
Ooh, so break into blocks. That's right. That's a very interesting idea. Remember that for next time. What if we break our signal into blocks and then compute, the linear convolution, right? Then we can do that in real time. So we'll only have the delay of a single block. But there's subtleties. Okay? And we're going to talk about those subtleties next time when we talk about the overlap and add and overlap and save methods of how to compute filtering using the DFT. Okay? So see you on Wednesday.